When a storm unleashes a strike like this, tens of thousands of amperes bridge the gap between the clouds and the Earth in a fraction of a second. It is raw, immense power. But that flow of atmospheric charge is entirely transient. It bursts violently and then stops, making it useless for the continuous operation of electrical devices. For the electronics we use every day, like a flashlight or a wall clock, we need charges to move in a smooth, steady manner, much like water flowing calmly down a river. To maintain that steady current, we rely on a specific mechanism to constantly push the charges through the circuit. We call this device a cell. By the early 19th century, researchers figured out how to harness this continuous power chemically. They stacked dissimilar metals and saltwater-soaked cloth to force a steady electrical flow. A basic electrolytic cell works by placing two electrodes, one positive and one negative, into a chemical solution called an electrolyte. As these electrodes sit in the fluid, they exchange charges with the surrounding electrolyte, building up a relative potential difference between them. When the cell is entirely disconnected from a circuit and no current is flowing, the total potential difference between the positive and negative terminals is known as the electromotive force, represented by the Greek letter epsilon. Despite the name, electromotive force is not actually a mechanical force measured in newtons. It is strictly a potential difference, measured in volts. The term simply stuck around from before the physics was fully understood. While nature delivers current in chaotic bursts, the chemical cell provides the steady, reliable pressure required to drive modern electronics. But that steady pressure comes with an inherent physical cost inside the cell itself. Look at this used car battery. The physical wear on the casing and terminals is a good reminder that a real-world cell is not a perfect theoretical power source. The chemical electrolyte inside the battery has a finite resistance to the flow of charge. We call this the cell's internal resistance, denoted by a lowercase r. When you connect a circuit, current flows from the positive terminal to the negative terminal through your external device. But to complete the loop, that current must also flow backward, from negative to positive, through the resisting electrolyte inside the cell. Because of this, the actual voltage delivered to the circuit, the terminal voltage, V, drops. It equals the ideal electromotive force, epsilon, minus the current I multiplied by the internal resistance, R. That I times R term represents the lost volts. It is the energy dissipated as heat, just overcoming the internal friction of the battery's own chemistry. We also know from Ohm's law that the terminal voltage V must equal the current I times the total external resistance of the circuit, capital R. By setting those two equations equal, we find the total current in the circuit. The current equals the ideal electromotive force divided by the sum of the external resistance and the internal resistance. If you short-circuit the battery by making the external resistance 0, you draw the maximum possible current. But for most cells, this rapid flow of charge will generate enough heat to permanently damage the internal components. Moving forward, we have to treat every real cell as a two-part package, an ideal voltage source paired in series with a small, unavoidable internal resistor. To power larger devices, we often need more voltage than a single cell can provide. We achieve this by wiring cells in series, connecting the negative electrode of the first cell directly to the positive electrode of the second. For two cells in series, current I flows through points A, B, and C. The potential drop from A to B is epsilon 1 minus I times R1. The drop from B to C is epsilon 2 minus I times R2. To find the total voltage difference from the start of the chain at A to the end of the chain at C, we simply add the two individual potential turrets together. By grouping the electromotive forces and factoring out current, we can replace the individual batteries with one single equivalent cell. Its equivalent electromotive force is the sum of the individual epsilons, and its internal resistance is the sum of the individual internal resistances. If you happen to wire a cell backward, connecting negative to negative, the math still holds. You just subtract that cell's electromotive force instead of adding it. Wiring cells in series successfully scales up the total voltage push of the battery bank, but it also stacks their internal friction, raising the total resistance of the system and placing strict limits on efficiency. If instead we need to supply a larger amount of current without increasing the voltage, we wire the cells in parallel. This means tying all the positive terminals to one common node and all the negative terminals to another. Here is the schematic for two cells in parallel. Notice how the main circuit current I flows into junction B1 and divides into two separate paths, I1 and I2. According to Kirchhoff's junction rule, the total current entering a node must equal the total current leaving it, so I must equal the sum of I1 and I2. Because both parallel branches share junctions B1 and B2, the potential difference V across both is identical. Rewriting our real cell equations to solve for current and substituting them into our junction rule gives us a single equation linking both cells. By grouping the terms and isolating V again, the math reveals the rules for the equivalent parallel cell. First, the inverse of the total equivalent resistance is equal to the sum of the inverses of the individual internal resistances. Second, the equivalent electromotive force divided by the equivalent resistance equals the sum of each individual epsilon divided by its specific internal resistance. While the equations are slightly more complex, the physical result is clear. Parallel connections maintain the same baseline voltage, but effectively widen the pipe. They reduce the total internal resistance of the system, allowing the battery bank to safely deliver much higher currents to the load. These mathematical reductions are not limited to just two cells. The derivations for both series and parallel circuits scale infinitely to any number of cells, n, connected in a system. This gives us a powerful analytical tool, the black box. No matter how massive or complex a battery array is, mathematically it can be collapsed into a single equivalent cell with one voltage value and one internal resistor. This reduction is entirely made possible by strictly applying Kirchhoff's loop and junction rules to track the conservation of energy and charge across the network. As physicists first began to test these networks with early galvanometers and detection devices, they proved that these abstract mathematical rules governed the physical reality of the circuits. By learning to collapse complex grids into simple equivalents, we can calculate the exact capabilities and limits of any electrical network, long before the first wire is ever connected.